Hello, this is Jeongbom Jeong. I'm from Internet Computing Laboratory. Today, I'll talk about a paper identifying entity properties from text with Gaussian learning. It was published in 2019. Let's start. These days, entity plays an important role in modern search engines because there are a lot of entity-related queries, and number of entities are growing fast over the web. To enable a more efficient entity-centric search, new methods are introduced. Entity card is one of those. We can see the entity information, such as a short description and a set of facts. In this figure, the red box is the entity card. We can see that easily in one of the search engine, Google. Anyway, to provide entity information relevant to the user's need, an important task is identifying entity properties such as album and genre of the entity Taylor Swift from textual information. For example, given the text 2012 album Red took Taylor Swift's popularity to new levels, and the universal appeal of I Knew You Were Trouble was a key part of that success. In this sentence, the task is to identify the property album and the property track of the entity of Taylor Swift. Identifying entity properties enables efficient access to relevant entity information. We can infer relevant entity properties according to the document clicked by the user. And then it can be used for composing a more relevant entity card and offering additional relevant documents. For example, if you click a document including content like this, we can estimate that you are interested in these two properties, album and track. Thus, we can offer an entity card including albums and tracks. And also we can suggest other documents describing these two properties. In addition, by the identifying entity properties, presenting properties described in each document is also possible on the first result page of search engine. Suppose that a user issues the query Taylor Swift career highlights. If the properties described in each document are presented on the first result page. It helps the user select the relevant document efficiently. Actually, if you search the query, you can get the result in the first page as you above. And then you can choose the best one efficiently. Therefore, identifying entity properties from text is considered as a fundamental task in entity-centric searches. In this study, they address the problem of identifying entity properties from text. Actually, this task is similar to relation extraction. The most promising approaches of a relation extraction involves supervised learning through distance supervision. In this case, the training sentences are obtained by utilizing triplets of the property in knowledge base. Some properties correspond to a single predicate, and if sentence contain the subject Taylor Swift and contain the object her album like this, those are used as training example of it. On the other hand, the other properties correspond to a predicate path. In this figure, the path including music artist track contributions and music track contribution track is a predicate path corresponding to property music artist track contributions music track contribution track of the entity Taylor Swift. Thus, for this type of properties, a set of triplets, including their predicate path, is used to training sentences. This distance supervision approach is efficient for preparing many sentences without manual annotation. However, since obtaining the trained sentences rely on the triplet in the KB, there is a problem. Of course, many properties like this can obtain the training sentences from the knowledge base like this. But in case of certain properties, it is not. They can't obtain sentence for training. Thus, it is not practical to prepare training sentences for all properties. Lack of training sentences makes some problem with learning text pattern. The property without training sentences can be trained in the learning model. This problem is Gersha problem. Since Gersha learning, there are some problems. First is dealing low coverage of properties founded in sentences. Second is missing important information about entity. To address these problems, we can utilize property embeddings constructed based on a knowledge graph embedding. This is the method for identifying entity properties in this paper. Before the talk about this, we should remember last class. Last lecture, Professor said words can be represented by vector. For example, if there are words like, dislike, love, and hate, these can be represented like this in vector space. Then we can see that similar meaning words are located near each other. In the case of sentence and triplet, it is almost the same as above. These also can be represented by vector. Thus, if we want to identify entity property in a certain sentence, transform the sentence into representation and map to property embedding space based on knowledge graph. Then we can identify property by finding nearest property embedding. That is the basic concept of the method in this paper. Let's see more details from now. First part is property embedding. Before I talk about this, there are something we should know. Those are property characteristics. We can get the properties according to the structure of the KG, which represent linkages between collections of triplets like this. In this figure, those are triplets. It's also same. In this page, I'll talk more details about triplets. Actually, each triplet comprises a subject, predicate, and object. In triplet, the predicate represents the relationship between subject and object. For example, if there are subject Chong and object Seoul. The predicate live in represent the relationship between Jung and Seoul. And the subject can be an object of another triplet, like this. Whereas the object can be subject of another triplet. Accordingly, these typical graphic characteristics allows exploration between subject and object through the predicate path. So we can get properties we need from them. To obtain the embedding of each property, we use representations of subject, predicate, and object obtained by the cage embedding techniques. As mentioned earlier, we expect that the property embeddings will be close to each other in the embedding space if the properties are similar. Although the properties are constructed from the predicate, only representations of the predicate might not well represent the similarity among seen and unseen properties. Thus, we used to incorporate representations of subject, object, and predicate. Anyway, there are techniques for formulating embeddings. The first is SUM-R, summation of representations of predicates in the predicate path. If there are predicates in the predicate path, get the representations of predicates, and then we can get the embedding by summation of them. Second is CCSO, concatenation of the average of the representations of subject and object. By using subject and object, get the representations and then average them. Finally, by concatenation, we can get embedding. The third is CCRO, concatenation of the representation of the first predicate in the predicate path and the average of the presentations of object. In this technique, we are using only first predicate and object. First, by using object, we get the representations and then average them. In case of path, we are using only relation 1. By using it, we get the representation And then we can get the embedding by concatenation of them. Final one is CCSON, concatenation of the average of the representations of subject, object, and neighbor object of neighbor predicate of the last predicate in the predicate path. Actually, this is almost similar to the second method, but it just consider a neighbor object more. Anyway, by utilizing these methods, we can obtain the embedding of each property and construct the embedding space. In this page, I will briefly explain about model in this paper. This figure is the neural network-based model for multi-level sentence classification. In the first section, sentences are transformed into representation. Each word in an input sentence are transformed into a low-dimensional word vector here. And BLSTM models a sequence of words and produce a sentence level representation here. So we can get the representation of sentence in this section. And in the second section, proceeds mapping the transformation of a sentence representation and property embeddings based on a knowledge graph. And here, through filtering by entity type and obtaining probabilities by sigmoid function, finally, we can get the best option of the entity property of the sentence. From now, I will explain sentence representation and mapping space more intuitively by using this figure. When the sentence X is given, we can transform it into representation in vector space. After that, by using the equation Q, including weight matrix and bias, map the sentence representation into property embedding space based on a knowledge graph. Then we can see that the sentence is located to near property embeddings, music artist album and music artist track contributions, music track contribution track. And we can infer that the properties of the sentence are those. As a result, we can identify entity properties from text in this way. This is all of my presentation. Thank you for listening.